Good morning everyone, Dr. Nat here. So we are doing week 13 lecture for ECC 3129 and ECC 3119 for Electronic Communication Circuits class. So let's talk about digital communication techniques. We have talked about this in week 11 and we talked about, let's just do a little bit of recap. But for today's class, I would like to go over oversampling and undersampling in more depth, and then we will find out how to get the best sampling rate when we are undersampling and aliasing. Okay, so we talked about today's electronic communication. Most are digital because of the cheap A to D converter and D to A converter. We have that at our expense, so this is very much possible to make everything digital. So we talked about the benefits of digital communication, which are noise immunity, signal regeneration, error detection and correction. And then we had DSP, or digital signal processing. And what DSP does is really optimizing the analog to digital conversion by means of filtering, equalization, phase shifting, mixing, and other traditionally analog methods. And we have learned all of this. We've learned phase shifting, we've learned mixing, we've learned filtering. I did not touch on equalization, but basically these are DSP techniques. And then we briefly touched on parallel transmission of binary bits. When we transmit parallelly, we can have a really fast transmission. Parallel data transmission is extremely fast because all of the bits of the data are transferred simultaneously. Now this is common sense, but what limits this transfer? The shorter the length, the higher the speed. But if we want to do long distance, this is not going to be our best technique to use, because over larger distance, over longer distance, there will be crosstalk, and this will also limit the speed. So now we're talking about serial transmission of binary bit. We also talked about this week 11. So data transfers in communication systems are made serially, where each bit of a word is transmitted one after another. So this is in contrast to the parallel transmission, where each bit is transferred simultaneously. For serial, it does this one by one. So this figure shows a code of 1001101 being transmitted one bit at a time. So here, how it does this is that the least significant bit is transmitted first. Now what is least significant bit? This is going to be our least significant bit, the one on the most right. This is our least significant bit, and this is going to be our most significant bit. What does it mean when we talk about most significant bit and least significant bit? So if we can relate this to non-binary numbers, let's talk about a number that is in the decimal format. So I have 89234. So here, for this guy, this is an accumulation or an addition of 80,000, and I have 9,000, and I have 200, and I have 30, as well as 4. So this guy, or number 4, is my least significant bit, because this is like the smallest value for this entire string of decimal format. And this will be my MSB, because this is like the hugest number for this format. It's the same case for the binary format as well. So this guy will be our LSB, because it represents a very small number, whereas this number is going to be our most significant bit, because it tells us something that is this scale, very huge compared to the least significant bit. Okay, so this is our decimal format. What does the decimal format mean? It goes from 0 to 9, and then 10 to 19, and then 20, etc., etc. So that is our regular numbering system. And in this case, in our transmission, we use binary. So it's a little bit confusing, but just remember that all numbers are the same. It's just a matter of formatting. Okay, so here the most significant bit is on the right, indicating that it was transmitted later in time than the LSB. So here this is our MSB and this is our LSB. So if I would try to match this, I can see that the MSB is over here and the LSB is over here. So with time, the MSB is then transmitted a bit later than the LSB. So this is transmitted first and this is transmitted later. And this is, how do I know this? Because I'm looking at this arrow which tells me time, which means that going to the right is increase in time. So this is going to be assuming this is 100 seconds and maybe this is 1 second. So with going to the right tells me that it happens after a longer time. So MSB is transmitted later, LSB is transmitted first. Now, how do we do parallel to serial transmission of binary bit? So shift register is a sequential logic circuit made up of a number of flip-flops connected in cascade. So this is our shift register. If you've studied computer architecture, you know how this looks like. You know what this is. But that's okay. I'm just going to go over it again. So with every clock pulse is applied to the flip-flops, okay, the bits of the word are shifted from one flip-flop to another in sequence. Basically, what it is doing is it's just pushing and pushing and pushing. So here we started from here. First clock pulse is going to push this entire string to the right. So I am transferring this first guy. And then the next second clock pulse, I am pushing the next guy. And then third clock pulse, I am pushing the next guy. And this next guy is received here, and this is now here, and this is now here and here. So I think this is quite intuitive. It's just pushing blocks of numbers one at a time. It doesn't disappear. It has to end up somewhere. So just push it to the right place, right? So the last right-hand flip-flop in the transmitter register ultimately stores each bit in sequence as it is shifted out. Once this is full, you will get your parallel data output. Okay, so then we talked about data conversion, whereby we convert analog to digital, and then from digital to analog as well. So modern ADC is usually a single chip IC that takes an analog signal and generates parallel or serial binary output. And then we talked about the sampling of an analog signal. Basically, sampling needs to be at regular time intervals, which tells us TS or FS. This is sampling time or sampling frequency. When we have a frequency, it tells us that this happens at a fixed rate. When we do this, when we do sampling, the continuous analog signal is now translated to a series of discrete binary numbers representing samples. So when we sample, we are taking the value at this point. And these values are translated to be maybe 0, 1, 1, 0, 1, 1. I don't know. This is just random. But each level tells me something, tells me a value, and I will use this value as my digital signal. So for sampling to be efficient and retain all the information from the analog, we need to follow the Nyquist law. And the Nyquist frequency is basically Fn or the Nyquist frequency needs to be greater or equal to at least 2 of the 2 of FM, where FM is the frequency of the input signal. And then we have another condition for bandwidth limited signals with upper and lower limits of F2 and F1. The Nyquist sampling rate is just twice the bandwidth, or 2 F2 minus F1. So this is the first condition, and this is the second condition. So what this means is that for the first condition, we are assuming that the signal starts from 0 or DC, 0 Hertz, up to FM frequency. Maybe FM is 50 megahertz. So the Nyquist law, or the Nyquist condition, tells us that Fn needs to be equal or greater to 50 megahertz, and therefore our Fn is going to be at least, this is going to be 2 times 50 megahertz, so it's going to be greater or equal to 100 megahertz. So this is for the first condition, where we assume that the signal starts from the DC and has signal up to FM 50 megahertz. Now, for the second condition, let me duplicate this. Okay. For the second condition, we have a situation where the FM is in the middle of the spectral band, like that. We have seen this in AM signal, and this guy has some sidebands. Let's say this is 20 megahertz, and the FM is 50 megahertz. So this will give me a signal between 70 and 50 minus 20 is 30. So my bandwidth, what is my bandwidth? My bandwidth is 40 megahertz. So the Nyquist law, or the Nyquist condition, tells me if my signal is in the middle of a spectral band and is limited by a lower and upper frequency, I need to use this formula instead. So therefore, Fn is going to be 2 times 40, or it's going to be 80. Okay. And then we also talked about the Nyquist frequency example. So assume that the output of an FM radio is to be digitized. The maximum frequency of the audio in an FM broadcast is 15 kilohertz. So this is assuming that this starts from 0 hertz or DC up until 15 kilohertz. So we will use Fn needs to be greater than 2 FM, right? So in practice, the sampling rate should be higher, at least 2 times, but in this case, they say 3 to 10 times, which is still abiding to this condition. In practice, the sampling rate is much higher than the Nyquist minimum, typically 2.5 or 3 times more, right? And then what is the limitation of Nyquist frequency? The actual sampling rate depends on the application. We know that the higher the sampling rate, the higher the cost, the higher the complexity, the more channel bandwidth that we need, and hence we need more advanced circuits. So another factor in the conversion process is that because analog signal is smooth, it basically has infinite number or points, and we cannot translate all these points digitally. So we will have to take the best sampling rate so that we still retain all information, but at a cost-effective way. So an 8-bit binary can only represent 256 states, which may be the converted value from analog waveform, having an infinite number of positive and negative values between 1 to positive 1 to minus 1. So imagine we are starting from, okay, let me try to draw this. I know I've done this in class. I just want everyone to have a second view at this in case they were not following in week 11 class. So basically I have this type of signal, and this signal is now going to be digitized using 256 discrete levels. and I can